Welcome to qnawire.
Hello everyone. In this problem, we're investigating the effects or the motion of a pilot in a disorientation trainer. There's a modern version that is allowed to move the cabin of the device in the radial direction as well as in the circular direction. So what that means is that essentially you're allowed to exhibit a motion that is similar to what I've drawn here in terms of the trajectory. So in fact, in this problem, we're given that r, the radial direction, or the distance from the origin of the pilot, is 10 plus 2 times cosine of 4 times t, and theta is 0.1 times 2 times t squared minus 1. And we're also told that the mass of the pilot is 175 pounds. So in part A, we're asked to find that at t equals 5 seconds, what is the magnitude of the net force acting on the pilot? So if you think about what this motion is like, since theta increases quadratically, it means that the pilot is moving around quite fast. And so the angle that the pilot's position encloses with the horizontal just keeps increasing and increasing. And the radial position of the pilot fluctuates as a cosine function. So that means that it's going in and out, in and out, in and out, in and out as it moves around simultaneously. So then in order to find F net, we know that F net is going to be equal to the mass times the acceleration of the pilot. This is just Newton's second law. So what does the acceleration of the pilot look like in radial coordinates? So if you think about this now, we're moving in a plane, so we can use polar coordinates, so r and theta. And so in terms of that, the acceleration of the pilot looks like r dot dot, which is second time derivative of the radial component, minus r times theta dot squared. This is acting in the radial direction. Plus, so that's a plus sign, plus 2 times theta dot times r dot, plus r times theta dot dot acting in the tangential or theta direction, times the mass of the pilot. So in order to find what this expression is, we have to find r dot dot, theta dot, and theta dot dot, which I've given you over here. So this is just differentiating both the function of r and the function of theta as a function of time with respect to time. And then if you do that, then you can plug in the result of these derivatives into F net, and you find that F net is equal to this expression over here. So it's minus 32 cosine 4t minus, in brackets, 10 plus 2 times cosine 4t times 0.4 squared times t squared. And that's the radial component of the force, so that's Fr. And the theta component, F theta, is 2 times 0.4 times t times minus 8 times sine of 4 times t plus 10 plus 2 times cosine 4 times t times 0.4 times, and everything times the mass of the object. So then if you want to find the magnitude of the force, then you want to find the absolute value of the force. Now the absolute value of the force since the vector is equal to the vector, is taking the dot product of the vector with itself and then square rooting the result and evaluating it at t equals 5 seconds. So this is equal to Fr squared plus F theta squared, which turns out to be 61.6 pounds times feet per second squared. You can convert this to newtons by converting the pounds to kilograms, feet to meters, and then leaving the seconds as seconds. Okay, and then in part B, you're asked to plot what the magnitude of each component of the force looks like. And so this is what that looks like. So for Fr, for the radial component, you see that this follows essentially, basically it's an oscillating cosine or absolute cosine on the trajectory of or like modulated or enveloped by an r squared function or a t squared function, whereas the theta component just keeps increasing and increasing. And so that is the answer. So this is the Fr component, and this is the F theta component.